an avalanche of people. I don't see an avalanche of people rushing to join at this moment. So welcome to the ENA session of the ISP workshop. And for some reason, there we go. Okay, so I'm just gonna say a few words about logistics to start things off. Then we'll have a talk. We'll have talks by Eberhard and Costas. They should be short talks, kind of to set the stage of discussions about ENA measurements on an interstellar probe. Marov is asked to say a few words about SHIELD, and she's on to do that. I'll then take a very short time to talk about the mission and sort of setting the stage for discussions about what kind of measurements we should and can make. And then we're going to just dive into the Google Doc and talk about measurement objectives. And I hope that will be a discussion rather than a presentation. As far as logistics, this is the slide that I have been given to sort of make everybody play nice. Keep your audio muted when you aren't speaking. We're at about, what, 44, 45 people. It's a fairly large room. So we're going to ask that you use the raise hand button for now so that we can keep the crosstalk to kind of a minute. Whoa, okay, to a minimum. You can also use the chat to talk to the room and ask your questions. We have a moderator. He'll be keeping an eye on the chat as well as I will. We also have a Google Doc, and I would ask James to put the link to the Google Doc in the chat, and that will be available for probably the next couple weeks as a way to document our discussion. Everybody in the room can edit it. Please don't. Please be a good citizen and edit your own content. But what we're trying to do with that document is capture the ideas and feedback from everyone here. Okay, and from there, I'd like to kick off the talks. Eberhard, if you're ready, you can just grab the screen and go.
Thank you. Yes, I'm ready. So I'll grab the, oh, this will stop other screen sharing. Okay, I think I should be able to continue. Okay, and then I have to, yeah, that desktop share, and I hope it works. That
looks good.
Yeah. So, do you see now the full screen of that of the
Yep,
presentation?
you're on.
Pardon?
You're good.
Okay. Yeah. Since sometimes then I'm showing the presenter tools, which I don't want. But it's, okay. So I was asked to give a brief introduction to ENA observations from an interstellar probe. And so I would say that to boldly go sometimes, hopefully not too distant future. And I want to put it into a context of what we have right now with spacecraft with some interstellar objectives. So currently 3 spacecraft are on interstellar trajectories and operating. Voyager 1 and 2, as far as we can see outside the heliopause, New Horizons past Pluto in the Kuiper belt, and as always, all delivered surprises and puzzles. But I want to remind everybody, these 3, they were never built as interstellar probes, and they will definitely turn silent before the pristine interstellar medium. In the inner heliosphere, we have Ena imaging. That's the topic we are talking about. We're looking basically inside out, a full view of the sky. And here you see several couple energies and 2 time ranges, solar minimum, solar maximum from IBEX. And you clearly see the ribbon in all of those. And there is some distributed flux in between. And the ribbon was a big surprise when we saw that. Now we are working on IMAP. It will provide tracking of the interstellar wind, which we don't have on IBEX. We see it only in spring. We have full energy coverage all the way to the more energetic ENAs, thanks to IMAP Ultra, which is derived from the Inca instrument on Cassini. Will have higher resolution and collection power, and this will be combined with pickup ions and their acceleration. Now, one of the big questions for the heliosphere is how does the ISM control the heliosphere? And here Voyager 1 and 2 showed that the interstellar magnetic field plays an important role to shape the heliosphere. And Merav and Vlad, I saw him, they have worked on this tirelessly ever since then to see how that works in. Now, the key questions remain really: how is the magnetic field draped around the heliosphere? How does it interact? How is the interstellar plasma diverted and filtered? Which processes control all this, in particular the ribbon formation? We can get a lot of answers with ENAs from inside, and that will be done with IMAP, where we want to get a little bit of an inroad into the 3D structure. But really, to get to the bottom of this, you need to venture out with an interstellar probe. As one example, so I talked briefly about the ribbon and then the globally distributed ENAs. The ribbon is tied to the solar wind structure in latitude and its temporal evolution. And out of over a dozen models, basically the ones with more direct interaction with the solar wind have emerged as the most likely one. In particular, the secondary ENAs, which put the ribbon outside the heliopause into the outer heliosheaths and beyond. We know this as inference from the solar wind evolution and parallax measurements, which still have a large error bar. The biggest challenge for the ribbon is really the pickup ion ring around this interstellar magnetic field. You need that to keep the ribbon in place. That seems more stable than theories predict, and people have worked on various models how the instabilities could be suppressed, or whether there is a spatial retention of the pickup ions due to strong scattering or trapping in the interstellar turbulence. Now, key observations will be in situ ions and field measurements. If you go somewhere through the ribbon, and orthogonal ENA imaging of the morphology. So that's the field of view of an ISP going out with the field of view perpendicular to the trajectory. Now, you might ask, oh, you would only see the ENAs that come from this pickup ion ring parallel to the magnetic field. You won't see anything. Well, that's true. Let's look into the cut in the orthogonal plane here. and you see the magnetic field basically head on, and then you will see this with the field of view, and you can basically take a look what's the pitch angle width more locally, and what is the extent of the retention region out of this plane here, or in that plane, and also from the heliopause all the way out. Where does it stop? Where does it start? And also, Inca has shown us the belt. Is it related to the ribbon? Where is the belt? Is that already inside the heliopause? Well, if you look perpendicular, you can figure all this out as, on your way out with the interstellar probe. Now, going through the ribbon, that presupposes a certain direction, and well, it comes together with getting out of the heliosphere at the shortest distance, so that you can get fastest into the pristine interstellar medium. And if you go somewhere close to the nose where the magnetic field helps, you go through this maximum pressure region. And by the way, that's uncharted region from the Voyagers. They are about here and here. They are going on both sides of the ribbon and both sides of the maximum pressure region. So if you go through there, well, you can immediately see that you get a perpendicular scan of this region, which houses the globally distributed ENA flux, and you can obtain a radial profile and the thickness. And if we happen to have the ENA sensor, if they are like on IBEX or IMAP, 1 pixel cameras, and on a pivot platform so that you can move them, or you have something like Inca or IMAP Ultra that has a field of view so over this range, you can get various cuts through the inner heliosheath, and you get really together with that. That's another important point. You want to have something like IBEX or IMAP in the inner heliosphere to continue taking this view. So you get to really the 3D map of, or not map, the 3D structure of the heliospheric interface region. Now, if the ISP would go out somewhere between Voyager 1 and 2, it will go through the ribbon, and it will go through the region of the belt, and you get a stereoscopic view for all of these structures, and as well as I showed for the globally distributed ENAs. And one more little plug, the neutral solar wind and ENAs from the heliosphere, they are likely the strongest solar polluters of our neighborhood. The anomalous cosmic rays, they are found by the Voyagers substantially reduced outside the heliopause. But what we are talking about here with the ENAs, that's the strongest polluters outside, and that's must affect somehow our neighborhood. And here's the summary of the points that I wanted to make. And I just want to hammer on the last point, together with a continuing heliospheric imager like IMAP, the ISP will provide a full 3D view. Thank you.
Okay, do we have any questions? You can either raise your hand or type them in chat. and Pontus.
Very nice. Thank you very much. So just a couple of questions to simulate the discussion here. So once we go through the ribbon, what, and you don't have to answer it now maybe, but we got to think about what are really the measurement requirements on the in situ part of the payload in terms of pitch angle resolution and things like this.
Well, Pontus, that's a very good question. And I built this talk from a talk that I gave it's 2.5 years ago now at the Coast Bar. And at that point, I put the main focus on the in situ measurement. And I think if you're going through the ribbon region with these different models that all address the pickup ions in the outer heliosheath, what you want to definitely measure is the pitch angle distribution of these pickup ions, and you want to get a good measurement of the magnetic field fluctuations out there. We have measurements from the Voyagers that's outside the ribbon region. So you can directly compare, do these pickup ions generate additional turbulence inside the ribbon region? That would speak to these strong turbulence that's self-generated, that produces a spatial retention region like McComas and Schwadron have talked about, and Phil Eisenberg has come up with a model. If it's the same strengths of this, that might go more in line with the model from Jacobi and Giacalone. So just as an example, and this together with the actual pickup ion there, and then supported by the ENA view perpendicular, where you get the integral view through the ribbon in a direction orthogonal to what we hopefully continually see from the inner heliosphere, we should definitely be able to nail what this is all about.
And I've just one more quick comment. I don't know if you picked it up in my overview presentation, but right now we are carrying what you already mentioned, I think, and that's a scanning platform for an IMAP-like, IMAP high-like instrument, and also a wide field of view instrument.
Okay.
Yeah, that's very important.
Yeah. No, I think that is very important for providing a full 3D view of at least the forward hemisphere of the heliosphere. How is the inner heliosheath shaped? How is the thickness changing all around? I think that can be addressed with scanning through these regions perpendicularly up to maybe 45, 60 degrees backwards from the along the trajectory. And then again, together with continuing imaging from inside the heliosphere.
Okay, we have a question from John Cooper in chat. Determine upper limit on VLI, ISM, ENA fluxes from external sources. Field of view parallel to B helps.
John, what do you mean by external sources? So with ENAs, what makes them so perfect for the scanning the heliosphere is that the mean free path for charge exchange is of the order of the size scale of the heliosphere, namely several hundred AU. And the flip side of this is that all really external ENA sources from far away, you're looking into an optically thick for ENA's regime, and these sources really don't matter. What really stands out is the stuff of the heliosphere and immediately around the heliosphere.
Does that answer the question? Okay, I've got to assume that that covers it. And
Yeah, he said okay.
oh, okay. And I think we should move on to the next talk. Oh, wait, we have a question from Eric. How close to the solar direction can you measure to detect any changes in the flux of neutral solar wind?
Well,
that's a deep question.
That's a deep question, and so far we haven't built ENA instruments that really would want to look towards the sun. Say, for example, on IMAP, we will be taking great pains of making sure that IMAP low will never look into the sun, even during the transition of trajectory or so when it's not on, because there is a potential suspicion that contamination on the conversion surface together with UV that would crack hydrocarbons could have made a difference right in the beginning of IBEX before we even turned it on, since the efficiencies seem to have changed from what we measured in the lab. So that's one thing, and then the closer to the sun you go, the more distractors and background you have. So I don't have a really threshold answer here, but certainly I think one would want to push that, but it's tough.
Yeah, I will add that the direct measurement of the secondaries is in the science traceability matrix, and that the difficulty of the measurement along with making other measurements is certainly in play at this point. It would be an interesting thing to, it would be, I think, a really valuable thing to measure. The question is whether it's a conceivable, it's a practical measurement or not.
Well, I would agree, in particular, speaking to the one point that likely the neutral solar wind is the biggest polluter to our immediate galactic neighborhood. But probably what this would be that it should be a separate instrument or a separate section of the sensor that has provisions against the solar radiation, etc.
This is an interesting discussion, but I think that we should delay that until we're talking about it in the STM in particular. And let's move on to Costas's talk.
Yeah. Okay. Thank you. So I will mute myself now.
Thank you very much, Eberhard. I thank you very much.
Okay. You're very welcome. My pleasure.
Okay. So hi, everyone.
So stop share. So
yeah. Okay. Okay, can you hear me?
You're good.
Yes. Oh, okay, thanks. Okay, so thank you very much. And this will be a very brief overview of ENAs and ions in the heliosphere, mostly from the perspective of the Cassini-Mimi measurements, Inca measurements, and the Voyager 1 and 2 measurements. So let me get straight to the point. And these are full sky images of ENAs in the KV energy range from Cassini, organized in ecliptic coordinates, and they are centered at the nose. Now, these images show the existence of a so-called belt. That is a high-intensity ENA region of enhanced particle pressure that encircles the sky sphere and corresponds to a reservoir of particles inside the heliosphere. And we also identify two prominent basins, which are these blue areas in these figures, where the ENA minima occur, and that they also originate in the heliosphere. The black lines that are on top of these images outline the low energy ENAs from the IBEX mission and show the location of the ribbon that Eberhard talked about before, which is thought to lie beyond the heliopause and sits on top of a so-called globally distributed flux, which is produced mainly in the heliosphere, but perhaps not entirely. So clearly the ribbon and the belt look very different, so different ENA energies, so divergent views for the heliosphere. But we know that the ribbon broadens with increasing energy, and at high energies is shown to match the ENAs from Cassini, as is briefly outlined here. So what happens to the ENAs with time? After 16 years of Cassini observations, we have verified that the ENA intensities from the belt in these yearly maps are reduced till at least the years 2012 to 2013, and then begin to recover up to the year 2016. Now, notably, this decrease is global throughout the heliosphere, and there is also a corresponding variation in the ENA spectral index that I'm not showing you here. So the in situ measurements inside the heliosphere from LECP, which is the figure in the middle, show the same time variation as the ENAs from Inca in overlapping energy bands. There is a decay from up to the year 2013, that is a local minimum, followed by a recovery. So as far as the upwind hemisphere is concerned, towards the nose, I mean, we also observe a similar situation in the ENA intensities from IBEX at roughly the same time periods, especially if we're looking at the highest IBEX energy channel. And all these ENA and ion variations correlate well with the solar wind energy flux and pressure at 1 AU that declined over solar cycle 23, showing a local minimum at about the years 2009 to 2010, and followed again by a recovery. So the inference here is that the dynamic properties of ENAs and ions from the heliosphere are strongly related to the dynamic properties of the solar wind itself, as measured at 1 AU, with a time delay of about 2 to 3 years, or perhaps more. Again, notably, the modulation of the ENAs over the solar cycle seems to be global throughout the heliosphere. So the interstellar probe should take high time and spatial resolution ENA images and in situ ions over a broad energy range and from a changing vantage point over at least a solar cycle. So these are energy spectra from Cassini. This is the green line that can be converted to ions, which is the white line in this figure, using standard parameters, and they can be compared directly with in situ measured ions from LECP, which is the blue line. This is a brief demonstration of what we call ground truth. So what is important here, among many things, is that the resulting ion spectra in KV energies inside the heliosphere are much more complicated than a simple Maxwellian or a kappa distribution. And this is important because now we know that we cannot neglect these ions when considering the pressure balance inside the heliosphere. In fact, the Voyagers showed that a substantial part of the solar wind energy at the termination shock was transferred into heating pickup ions and energetic protons. So this may well be translated to the prominent hardening break in the Inca and LECP energy spectra that you see in this figure. So the figure at the bottom demonstrates that the energetic particle pressure is significantly higher than the magnetic field and plasma pressures throughout the heliosphere. And if we miss such measurements in an ISP mission, we will miss a substantial part of the processes that govern the ion energetics inside the heliosynth. But then again, this is not the full picture here. And through the SID collaboration, we were able to produce a more complete picture. So the lower group of measurements, that is the orange, blue, and white lines here, are ENAs from IBEX and Cassini. Note that the turquoise dotted line that shows the converted LCP ions to ENAs in an energy range that will be covered in IMAP, and surprisingly, they fit smoothly to the ENAs from Inca. So the in situ measurements in this plot come from LCP, which is the turquoise line, and CRS, the green line. Now, when we convert all ENAs to ions, so we're looking at the upper group of lines, this group of lines describe an average ion spectra from 10 eV to 344 MeV, which is quite extended energy range. And it shows a number of hardening and softening breaks, which should be studied in detail as they possibly point to different processes in the heliosynth. And this is directly related to several science goals from the Interstellar probe. But these spectra provide also a unique opportunity to estimate the contribution of each energy to the total pressure inside the heliosynth, and also estimate the pressure balance at the heliopause. Now, in this process, and I'm talking about the figures at the bottom, we find two important things, among others: that the plasma beta in the heliosynth, as Merav mentioned earlier, is always far greater than unity. It's actually more like far greater than 10 throughout the heliosynth, so at least in the upwind hemisphere. And so the upwind hemisphere at least exhibits diamagnetic behavior. And that the total magnetic field that is required at the boundary in order to balance the heliosynth pressure is about 0.67 nanoteslas, which is what was measured as soon as Voyager 2 crossed the heliopause. So it is important to realize that imaging the heliosphere in ENAs essentially translates to imaging the pressure of the global heliosynth. And the combination of such measurements with in situ ions can reveal the acceleration processes inside the heliosynth, and of course the force balance that forms the entire solar bubble. So speaking of our solar bubble, when the Voyagers became interstellar missions, we identified that the interstellar flow is not the primary driver of the interaction of the heliosphere with the local interstellar medium, but it is the pressure of the interstellar magnetic field that mainly configures the heliosynth. So based on the evidence I briefly shown here, the Inca and Voyager data argue for a roughly symmetric diamagnetic bubble-like heliosphere. So the heliotail may be distorted in this view and extend to a few hundreds of AU, but not to the tens of thousands of AU as in the traditional comet-type configuration that is shown at the bottom of this figure. So this concept is also consistent with ENA measurements from IBEX law and also galactic cosmic ray models in the heliosphere. And also we have also these recent MHD modeling that show this exciting configuration with two jets towards the poles that do not merge into a single comet type tail. In fact, the tail here extends to a few hundreds of AU, something like 400 AU or so. So we have very different views for the heliosphere. And what has happened to the 10,000s of AU heliosphere view? Well, the IBEX high ENAs are thought to form in a situation where the external dynamic and magnetic pressures strongly affect the heliosphere, producing a configuration that is consistent with the very extended tail of the order of tens of thousands of AU. At least this is the case when considering the low energy counterpart of the IBEX high ENAs. But if we consider the traceback times of ENAs at the highest IBEX energy channel, the heliopause location seems to point towards a more distorted bubble. And recently, in a paper that used the computation of Ulysses and IBEX observations, showed that the distance from the termination shock to the source of the 1 to 6 kV ENAs in the heliotail is at the order of about 130 to 330 AU. So recent simulations that are referenced at the bottom using different assumed shapes for the heliosphere show that the Interstellar Probe mission is the best possible method to address all these puzzles shown here, provided that the ISP will build on and extend all these measurements that are very briefly shown. So to summarize, we know that the high energy ENAs are created in the heliosphere, and we require high time and spatial resolution measurements to understand the ENA intensity variations and connect those variations to the solar wind properties. We also know how many ions it takes to make one ENA in the heliosphere, at least in the KV energy range. And I know it sounds trivial, but it's actually not. So we require now in situ measurements of ions in the direction of the belt and the ribbon to determine how the ENA signatures change as a function of vantage point and time over the solar cycle. And we also know that suprathermal particles are important towards estimating the pressure in the heliosphere. And we require all kinds of different measurements from magnetic field densities, plasma velocities, and galactic cosmic rays to identify and characterize the termination shock, the heliopause, the structure of the heliosphere, and of course, the global pressure distribution. And finally, I should highlight that the phenomenology of the heliosphere can only be addressed when taking all measurements into account, because we do obtain divergent views for the global heliosphere and different features in different ENA energies. So we cannot afford skipping a few in the Interstellar Probe mission. So I think that's all I have to say. So thank you very much.
Okay, we'll open the floor for questions. And I will ask the first one. How would you prefer to image or measure the belt?
You mean with, yeah, well, ideally you can do that with ENA imaging from inside. So I would ideally like to have the Interstellar Probe, for example, imaging the heliosphere as it goes towards the termination shock before the heliosphere, that is. And of course, that it would be interesting to see how the belt looks like from the outside, because of course we have never seen that. So we know that we can image the belt from the inside, so we don't know what happens when we step outside of the heliosphere, beyond the heliopause, I mean.
What would you prefer, to fly through it or at some distance to it?
I think that, you know, with the trajectories that are suggested from what I've seen, it's really hard to miss the belt because it's a very broad region. So whatever trajectory pretty much you deselect, you're not going to miss the belt. And I think I would prefer to fly through it, yes, because we also need in situ measurements during this particular time. As I showed, all these ENAs and ions work synergistically. So we need to have that. So yes, I would prefer to fly through it.
Okay. And we have a comment from Marov.
Yeah.
I would say that we should go sidewise to be able to probe the shape.
Well, yeah, in terms of looking the heliosphere from outside, the ideal, I guess, situation would be to go through the flanks. So you're going to miss the belt, and I think you're going to miss the ribbon as well, in that particular sense. But that trajectory would be better for imaging the heliosphere from the outside. Actually, the two, let me go back a few slides. Actually, those two simulations that I showed, that I didn't show, but I referenced, are showing that the best, they're taking, you know, different scenarios for different energies, and they're simulating how the heliosphere will look like from outside. And I think that the preferred trajectory would be through the flanks, if I'm not mistaken. One of these is yours, Bob, so correct me if I'm wrong.
No, that's correct. Mara, if you want to unmute and...
Yeah, I was looking, you know what I was looking for? The raise hand. and I can't find it, so I was chatting. I put it in the chat. I will agree with what Costa said, that going through the flanks is the best. But we had this discussion, I think, last year. I think you could go, exactly, this is what Andre is saying. You could go 45 off the nose, through the ribbon, and still through the belt, my understanding, Costas, you have to, and then you still will go through these interesting regions of belt and ribbon and be able to measure the shape.
Yeah, let me just show you here that if you go to about 45 degrees, which is, I hope you can see my pointer.
Yeah, we can.
Yeah, so if you go through there, you're not gonna miss the belt or down here, let's say. So that's about 45 degrees in the ecliptic latitude. So you're gonna fly through the belt, and you're gonna get the edge of the ribbon, I guess, in this particular trajectory.
Right. Let me remind you, if I may, of the baseline trajectory that we have fed into Jim's team, and that's the nudge trajectory. It is at 295 ecliptic longitude.
Where is that here?
And
I actually have a slide on that a little bit later.
Good.
Okay, yeah.
So we can talk about direction at that point. Andre, do you want to say anything about your comment? But I think that anything in addition?
Not really. Yeah, I mean, I wrote my comment, so.
Oh, I haven't seen that, so.
Yeah. Yes. Yeah. Sorry. I just. Anyway, so 45 degrees off the nose. It should be enough to do some global shape probing while still going through the ribbon and the belt. Yeah. All right.
Yeah, at 45 degrees, basically you get enough angle when you get outside to see both the nose and enough of the tail, I guess. So
yeah, or enough to see if there's a long tail or not.
Exactly.
But you wouldn't if you go with straight nose or upstream. But yeah.
Exactly. Yeah.
Okay, we'll pause a brief time for more questions. Otherwise,
Stop
we'll
sharing.
move on. Okay.
Yeah.
And I will start sharing again.
So I had a question. I wrote it into the chat because there's no raise hand here.
Okay, hold on. I'm fighting with the same interface that you are here.
So while you're working this, can I ask the question?
Please do.
Costa, I was wondering how the model of making the heliosphere a bubble goes with the notion that the plasma beta is large compared to 1, which would mean that the magnetic field in the outer heliosheath and around the heliopause isn't dominating the plasma. So it would likely be very much changed by the flowing plasma of the interstellar flow.
Yeah, so basically, in a nutshell, this goes in the sense that the external magnetic field, which is quite stronger than we expected it to be, interacts directly with this plasma in the heliosheath. So this is what, and it confines it in a sort of distorted bubble. So this is, in very brief, the formation. I referenced the paper when we discussed the details on that. But that's the whole idea in a nutshell.
Yeah, but so if the plasma beta is high, the importance of the magnetic field is, relatively speaking, much less than when you're close to 1 or even.
No, Eberhard, I think the plasma, let me jump in just for a second. Yeah. I think the plasma, if I understood your comment, the plasma beta is believed to be larger than 1, much larger than 1 in the inner heliosheath.
Yes,
in the outer heliosheath, this is not the case.
Well, I don't.
But when we're probably, at least in what we think with range of values of ISM and magnetic field, let's say a magnetic field at far away, like 4 microgauss that can reproduce what Voyager is seeing outside the heliosphere, the PB is around the PT. So beta is around 1.
So let me just say that when I'm saying heliosynth, I mean the region between the termination shock and the heliopause. I don't like using the terms inner heliosynth and outer heliosynth. So I guess I should have said inner heliosynth, as Merav mentioned, but I'm just using the term heliosynth.
Okay, okay.
Yeah.
I should learn to unmute. Thank you very much, Kostas. And we
Thanks.
will move on from here as soon as I can figure out how to work this thing. Okay. So we're gonna move on to what I hope is a more general discussion of the science for the interstellar probe. I have a few slides here to sort of orient everybody. They're almost all stolen from Pontus's talk yesterday, so I will go over this fairly quickly for those who were not able to see that talk. What we're engaged in here is a trade study. It's not an instrument selection or a payload definition. What we're trying to do here is to formulate the science, come up with kind of a straw man set of measurements that we would make to satisfy the science. What we're here to do is to basically come up with a set of mission concepts that can go forward and be submitted to an SDTT to better define a mission. We're doing this through a science traceability matrix, and right now that is embodied in a Google Doc that is tremendous in size and scope, and you know, you're always tempted to project these things, but I think that would be a losing proposition. What we're trying to do is capture the science and the science implementation for the mission in the science traceability matrix. And it is a Google Doc, so it can be community edited, and I would encourage everyone to take a look at it and to provide input. So this is the baseline trajectory slide that we talked about earlier. And that little green dot down here is kind of the current thought of where we're going, or at least that is the directions that the engineers are using for their analyses. The heat map below all this is the velocity that can be achieved with the powered Jupiter gravity assist. And you see that once you get above 30 degrees and out of the ecliptic, we really have the velocity really starts to drop off pretty quickly. There's this kind of sawtooth that we want to take advantage of, and what we're doing with this current trajectory is something that catches the ribbon, comes close to 45 degrees from the nose, and is near one of these velocity maxima. So that's where we are right now, but certainly we can still keep discussing the directions in which we go. And I'm sure that when we talk about the planetary collaborations with this mission, they will have some opinions as well. So right now, what we're baselining is a sun-pointed spinner. That's what we're studying. There are other options that can be done, but this is by far the simplest. And it's almost strictly heliosphere focused, pretty much because it's really hard to have a flyby camera on a spinning spacecraft that is that we could fly by a Kuiper belt object with and get useful information from. So we're talking about just a plain vanilla spinning spacecraft with long wire booms. Other augmentations would be, if we want to do flybys, we could 3-axis stabilize this thing and convert the booms to rigid booms. We would gain flyby camera type of things at the cost of shorter booms. There are other scenarios too that will be discussed later on in the week. This is our model payload. Again, we're trying to capture as much science here as possible. So, you know, we need to talk about whether this is sufficient or whether this is overkill for different science questions. I'm not going to talk to this too deeply, but if you have questions, be sure to ask. Another thing to really take into account is instrument accommodation. This is a picture of the notional spacecraft, and what you see is a 5-meter high gain antenna dish that is always pointed back towards the sun, which means anything that needs to look back towards the sun needs to be out on a boom. Keep in mind that if we do not go directly towards the nose, that anything pointed ramward will not necessarily be pointed towards the interstellar flow. And if we have to keep in mind that when we are inside looking out, the cameras have to be pointed out, and if we're outside and we want to look in, we want to be pointed inward. So all of that has to be balanced in terms of what our measurements are and the complexity of things like tables and moving parts and that sort of thing. The other thing to take into account is the data volume and communications. Mostly for this purpose, we've separated the mission into three basic areas. When we're in the inner heliosphere, for our purpose, that's 70 AU. From 70 AU to 250 AU, and then beyond 250 AU. Those present just different communication regimes, and by the time we're really out in the interstellar medium, we're more like having a telegraph than a cell phone, really. Okay, and so one of the things that we want to consider is what we want to do in these various regions where we have the communications available, both inner and outer. Now, we can start up the discussion. What I'm going to be doing is projecting the Google Doc that is kind of a distillation of the science traceability matrix. The link is here, and I believe I asked James to put it into the chat earlier, so it should be in there. What these are is the measurement objectives in approximate priority order. It's a rough priority order that I just got by some arbitrary sorting of the STM. We do want to talk about priority, but it's not something that we want to be wrapped around. And again, this is a discussion and not a presentation. How many people do we have? We have a little over 50 people. I think that if you want to unmute yourself and speak, that should be just fine. If it gets unmanageable, then we'll have to do the raising hand thing. But I think that we can probably get by with just having people unmute themselves. The inputs will go into the working STM. Again, the meeting is recorded and we have people taking notes, but what we really want to do is capture your comments for the long term in this Google Doc as well. So these are the things that we want to talk about: the science priorities, measurements, objectives, how we're going to make the measurements, how we separate them into phases, and the various logistical concerns of where we go and where we point and that sort of thing. And having said that, while I switch to the other document, if anybody wants to ask questions at this point, now is a good time.
This is Merav. I just had a comment that I put.
And I completely forgot to have you present your slides, and please do that now.
Oh, okay.
I apologize for that.
No, it's fine. It's fine. Let me just make my comment and then I can present really quickly the slides.
Yeah.
My comment is, I think and this probably, you had this discussion before, but I think in terms of trajectory, I am worried that emphasizing just IBEX, crossing just IBEX ribbon won't be enough to excite the broader community. We need the full support from different communities. So going through more to the flanks or 45 at least, you can get the folks that are interested in particle acceleration engaged. There is different plasma conditions there. The issue of the shape is crucial as well, not just for the heliosphere, but for astrospheres. And so this is my general comment in terms of trajectory. Repeating a trajectory very similar to a Voyager 1, Voyager 2, I don't think will get us with a broader engagement. Okay, let me just show my quick slides.
And Merav, as you get started, we've got 20 minutes left in this part of the day.
I have like two seconds. 2 seconds.
Great, okay.
Okay, so this is I just wanted to comment that when you do modeling in ENA maps and try to compare with observations, there is numerous assumptions that goes both from MHD models, both from what goes from the MHD models to the model DNA maps, and finally to compare with observations. So this is a can of worms that involved in numerous plasma processes. So just imaging ENAs and thinking you can get the grand truth is not true. You really need to pierce all these different processes. We're trying to do it within SHIELD. Costas has a paper that he mentioned when we're trying to get the full plasma pressure in the inner heliosheath. And we're trying to debate these different processes that produce ENA maps. And the other plug I wanted to make, that we have a younger generation shown here by Mark, Martina, and Igor from different groups that are trying to compare different MHD models and the assumptions that goes into these models, whether non-ideal processes are present or not in the models. We don't know. This is an interesting physics that, again, I think will excite a broader community within the inner heliosheath, and the effect on ENA maps. So all the way from IBEX to IMAP. So there will be a couple of papers coming out from this group where we're comparing the plasma processes and using the same boundary conditions with the models. So we can compare apples and apples and really pull out at least what happened when you include non-ideal processes. So this is within the SHIELD project. If you want to participate, please email me. Everybody is free to join our telecons and contribute as well. Thanks.
Okay, thanks, Marav. And I want to put, I want to speak a comment that John Cooper has made in the chat. It's important that the PLS energetic charge particle sensors cover the ranges of ENA, low, medium, and high. I think that's absolutely true. Okay, I am going to grab the screen back and hopefully find, hold on. There we go. Okay, does that look like the Google Doc?
Yep, we can see it, Bob.
Okay, excellent. And I have to rebuild so that I can see the chat again. Okay. So just to set the stage, these questions have this sort of color coding for the various measurements. This is the key for that. So we've separated things into the inner, outer, and interstellar. That's 70, 0 to 70, 70 to 250, and beyond 250 with the various energy ranges of ENA. We're talking low from 10 eV to 2K eV, medium from 0.5 to 15, and high from 1 to 100. These are generally IBEX, IMAP low, IMAP high, and IMAP ultra energies. And
can I have a question, Bob?
Sure.
Maybe I missed it, but are you thinking ENA only to go to IBEX high in the inner heliosheath, or I misread it, the M, ENA M? 15 kV is too low in the inner heliosheath.
Right. In the inner heliosheath.
Because we won't be able to see the tail.
Exactly, yes.
You need to go to ENA high
yes.
in the inner heliosheath as well. I hope this is the plan.
Oh, this is certainly the plan. This is what you see here is only the first question. And it looks like in the inner and outer heliosheath, we are specifying the use of the high and the medium instruments. Is that how you read that?
What I read, maybe I have to look at again more carefully. I read that the inner heliosheath are only going to go to ENA M, and this get me worried because.
No.
Okay.
The sequence is high, medium, low from left to right.
Yes. So, sorry, that's counterintuitive.
Yeah.
Oh, okay. Got it. Sorry.
Okay.
Stam Comedies, can I say something?
Please do.
I'm really confused about the choice of definitions of inner, outer, and interstellar, because I don't understand the basis on which these are made. As far as, are we talking about the limits, the physical limits of the heliosphere? If we are, then the inner heliosphere at most we can talk about around the Earth and a few AU. But the fact is that the outer heliosphere stops at the heliopause. That's the limit we know, and it's 120 AU. I think I heard 250 AU is the outer heliosphere. That makes no sense to me because we have measurements. We know essentially that both voyagers measured 120 AU, irrespective of solar cycle. One was solar mean, the other was solar max. So that's the boundary we know.
I'm going to agree with you that.
Hang on, these are boundaries that we have defined for our mission phases from an operational stand. Is that not right? Didn't Jim Kinnison lay that out yesterday?
Yes.
Yeah, so
okay.
I can take this.
Then we should make it clear that there are mission boundaries, but not call them by names that confuse the physical dimensions of the heliosphere.
Yeah, hi Tom, let me take this one.
When we talk about outer heliosphere 250 AU, how could that has no physical meaning. We know that beyond 120 AU, there is nothing there. Now, somebody asked, I don't remember who asked Merav, when does she think are we going to go to unwind, the true interstellar field? And she said, well, who knows, but maybe 400 AU. So again, that's the physics part. To say 250 AU as outer heliosphere makes absolutely no sense. Only, as I understand it now, it is stated because maybe we can commit to that as a goal from a mission standpoint.
Yes, so let me comment on that, Tom. This has been under much discussion, and this is not decisive, and we may change it. It was the first step, and as Michael already said, this is sort of to drive the mission design, and where the 250 AU comes from, sort of a first step at the sort of a minimum distance that one needs to go. But I agree also with you. I mean, it needs to better reflect and maybe be refined to actually reflect a heliosheath phase, where you limit that phase to the heliopause. So I do agree with you. And the jury's still out on this, and we need to we may refine this later to better phases to actually tie it to science.
I would like to make a comment on this.
Yes.
And that is that it's useful to have some word describe the part of the region beyond the heliopause that is not pristine interstellar medium in the sense that it's been affected by the presence of the heliosphere. So, I mean, at one point people were calling that the outer heliosheath, especially when we believe that there was a bow shock. But it seems like that's sort of gone out of favor to some extent. I kind of don't like calling it the very local interstellar medium because that term has been used for a much larger region, including all the nearby interstellar clouds.
Yeah, I think that's fair. We may actually never get far enough out into a pristine medium. But let us take it under consideration to rename these phases because they really don't reflect scientific boundaries. As far as I regard these as more of engineering. This is driven by the mission and not by the science at this point. So renaming them is maybe a good thing to do.
Okay, thank you.
I'm just looking at the chat here. I have a friendly reminder that we have 8 minutes left, and that was a few minutes ago. So I guess why don't we start here with the first question, and we'll just run this for another 5 minutes to look at the top priorities here. That is, remotely observe the ENA intensity variations of the Helios sheath, correlate those to changes in the solar wind properties. Does anybody have any comments on this? Measured from 0 to, or 1 to 250 AU. It looks like with an energy range of 0.5 to 100 keV. Okay. With no comments there, we get into the ribbon and the belt, which are we've set as high priority measurements, with the ribbon being measured by what we're calling ENA medium, that is 0.5 to 15 keV, and the belt with the high energy instrument. I believe the text for these is the same, interchanging the ribbon and the belt. I think Marov had some comments about the priority of the ribbon. As far as the ribbon goes, there's a great deal of value of in situ measurements going through the ribbon, but it does restrict us to the approximately 45-degree trajectory. Do we have comments about that?
Bob, I have some comments about these two boxes here. So since I saw that what you call the ENA medium and high, they have some overlap in the energy ranges, I would put a different symbol as kind of supporting measurement for the high in the ribbon, and for the medium for the belt in the overlapping range. Since I think one of the key important things is to see how these two features are related, if at all. And you can do this best if you really look at this with both instruments in the overlapping ranges.
Yeah, and it actually helps the engineers, because then you have a backup measurement.
Right. So you have
ribbon.
partial redundancy, in particular for such a mission. So I think I would strongly recommend that in all of the topics where say you may have one primary instrument and one secondary.
Okay, I believe we can make that change.
And can I comment also on that?
Yes, please.
Yeah, in the sense that we also get, don't forget, we get the ENAs from the belt from about 5 kVs and beyond. So what you're calling IBEX, the ENA medium, right?
Yes.
That goes all the way up to 15 kV. You should be able to get measurements from the belt in that instrument as well. So not just the ENA high instrument.
Well, that was the other part of my comment.
Yes, exactly. I'm just building
So
on that. Thanks.
The medium should be the secondary for the belt then.
Yeah. Yeah, I'm just supporting the comment that it's actually true that we do get measurements with Inca from about 5 kV of the belt.
Okay, I'm gonna Pavel has put in a comment into the chat. If you want to speak to that, Pavel.
Yeah, this is not directly related to these questions, but I just want to, I would say, to all these questions slightly together. So and in some points I see that there is expected that the ENA detectors are able to distinguish between hydrogen and helium ENAs. I just want to kind of point out that it's important to look into helium ENAs. And one thing is because hydrogen is attenuated in the list. And the other thing is that helium would enable potentially to look some sources in the list. So more of that is on my poster. I don't want to, you know, take more time on that from here.
Okay, thank you. And we are now at 12:50. We should really close this down, but before doing so, I'd ask if there are any more comments that anybody else wants to make while we're here. And please do look at the ENA, the Google Doc that's in front of you right now. Please check out the STM. And if you've got comments, certainly annotate both of those documents over the next couple weeks. Do we have any more comments?
Yeah, I mean, I made a comment at the bottom of the Google Doc.
Yes.
And we will continue this discussion basically right afterwards in 10 minutes. This discussion about what do we do with the low energies, basically about ENA low. As it currently stands, ENA low seems to be, well, a nice to have, but not really a vital thing because there's no black dot anywhere at a priority 1 a field in our color code. And yeah, we just have to be aware that, of course, I understand that having a separate ENA low instrument is a hassle because it means an additional instrument. But of course, we have to be aware of what we're losing if we forego an ENA low. Regarding the ISN, how to say, aspect of the whole thing, we will talk more about that in 10 minutes. About the ENAs, all I wanted to add here is please remember there's not only the ribbon and the belt, there's basically the whole globally distributed heliospheric ENA flux from everywhere. And if you look at the spectra, they go up and up and up. Below 1 kV, it goes up with a power law until it probably rolls over, but nobody knows for sure, around 100 eV. And there we have by far the highest heliospheric ENA intensities over your entire energy spectrum. So if we have no means of measuring ENAs below 0.5 kV, yeah, we're gonna lose out on some science related to ENAs. That's just, we just have to be aware of that.
Yeah, thanks for that. And please do, is that something that you're going to cover in your neutrals,
yeah,
group?
I will be covering, that was the ENAs aspect, so talking about heliospheric ENAs, this is why I mentioned it now. And regarding the stuff that's related to ISN, so neutrals, there we're also going to lose something if we don't have an ENA low imager, but this I will cover in basically 7 to 80 minutes.
Okay, thank you, and we should really close this down so that people can have a little rest before jumping into the neutrals. Okay, thank you everybody, and have a good day, and I thank you for your inputs.
Thank you.
I'm going to close this down.
Okay, it was great. Thank you.
Thank you all.
Thank you.